This is lecture 5 of CS147, section 01. We'll review second part of the Boolean algebra that we need for the digital circuit design. So last time what we discussed a few identities and formulas to reduce Boolean expression, and we have looked at the definition of a Boolean function. We tried to understand what the Boolean function is, and also we try to understand why in digital logic circuit design it is important to reduce a Boolean expression which implements a function. Okay, so to recall, like, we need to reduce Boolean expression by we need to reduce Boolean expression to reduce number of electronic component to implement that specific Boolean function. Now, if you realize what we discussed last lecture, that those identities and basic formulas for reductions is mostly for human consumption, means we are the one going to reduce expression, and we have to apply one of the rule part steps. Like there are like few steps, or maybe let's say there are n steps to reduce from a big expression into a smaller expression, and each step you will intuitively apply one of the reduction rule to steer the whole reduction process successfully towards the end, right? And there is no like systematic steps to do it. If you realize and if you have practiced a couple of examples, then possibly you have already came to a realization that there is no systematic steps. It's all depends on how familiar you are with the reduction process. You need to do a lot of practice, lot of intuition goes into it, uh, and to kind of successfully apply those rules at particular time at a particular steps in order to make the reduction successful. Okay, so it is completely human oriented process. Now, point here is this: when we design digital circuit, especially complex digital circuit, expression can be really huge, and it can involve like hundred of different variables. Okay, so it is humanly impossible to apply like this reduction process in a digital design steps as a digital design step. So the problem here is, like, we need to deal with lot more variables, and expressions can be really large, and it is for a human it is not possible to handle that kind of large expression to reduce down in more effectively and intuitively, right? And we also want to have more like an automated process, so that we can involve computer system and methodical computer programming to do that job for us, so that we can actually build up complex digital circuitry. Okay, that's the problem we are trying to solve. Now, to solve that problem, we have to come up with some standard algorithm, or at least standard method, to reduce and give an arbitrary expression, Boolean expression. Okay, this lecture will focus on that aspect. So, how we can formalize these reduction steps so that it's possible to actually write software program to do reduction for us. Okay, to do that we need two concepts to understand. One is standard forms, And second, one of the method we'll be discussing is the K-map. Now to note this K-map or Karnaugh map technique, it's again for almost for a human consumption. Okay, it's human oriented, but the point is that this method actually outline methodical steps for the reductions. Okay, and that served as the pioneer work to have more complex algorithms and steps towards multivariable Boolean expression reduction algorithm. Okay, so this we'll study this Karnaugh map, which is a stepping stone, which is a pioneer work towards development of more complex algorithm for expression reduction, which is very necessary for modern digital design softwares. Okay, so these are the two target for this specific lecture. Let's talk about standard forms. There are two types of standard forms. Okay, sum of product or SOP and product of sum, POS. Okay, so we'll whenever we refer a term SOP, it will mean sum of product, and POS, product of sum. Just to note that in this class we'll be more focusing on this SOP. Okay, SOP because we later established that if we can handle SOP and we can handle POS kind of automatically. By that, what I mean, sum of product and product of sum, they are practically kind of equivalent to each other. They just, the notion is different from each other, but they are a systematic representation of Boolean expressions, and they can convert from one to another very easily. Okay, we'll establish that they have a relation. So it is sufficient to learn SOP and for ongoing discussion. So that's why we'll be concentrating more on the SOP. All right. Now, purpose of the standard forms. First of all, it compact forms for the very large expression. A large expression can be like many terms, like maybe 2 pages, 3 pages long, stuff like that. We can very compactly express that. Also, it facilitates simplification process. So all the formal steps, all these algorithmic steps we'll be discussing in the K-map, it actually relies on the definitions and properties of these standard forms. Okay, SOP and POS. So that's the purpose. Now let's define that. Let's define this SOP and POS. Before doing it, SOP and POS uses like two different terminology. Okay, SOP is more related to the mean terms, which are the product term. So here, by the way, the product really means that dot operation, which we borrowed from the algebraic domain. It's a dot, we call it product, but it's really your AND operation in the logical sense, right? Your product is dot, dot is AND. So we loosely call it a product of term, but it is really a logical AND of the term, containing all the variables of the function appearing exactly once in their complemented or uncomplemented form. Okay, so mean terms, by definition, it is a product term, means it involves only the AND operations. It contains all the variables of the function in the complemented or uncomplemented form. Whereas max term are the sum term, and max term is involved with the POS style expression. So max terms are the sum terms. So here again sum has been used loosely in the very loose sense. Sum is like plus, plus is really or in the logical operation, right? So loosely we use the term sum here. So max term are the sum terms containing all the variables of the function appearing exactly once in their complemented or uncomplemented form. So that's the max term. Okay. Uh, we'll be looking at both of this term and how what they mean in detail in next couple of slides. But again, as this class will be more concentrating on the mean terms. All right. Now let's say I have a Boolean function expressed in a truth table, which is a function involving variable x, y, z. All right. So your truth table. So for timing, just forget about these two columns. Okay, this product term column and this symbol columns. Let's say we got a truth table of a function which like this. This is describing a function, right? So we are writing down all the combinations, Boolean value combinations of the variables and what are the outcomes for that basic function of these variables, right? And then we introduce, let's say, something called a product term. Okay, a product term we define like this will be using complemented form of that variable if it is value is 0 and uncomplemented form of that variable if it is 1. So here 0 0 0 we came up with x bar, y bar, z bar. This is the convention, like we are trying to define. This is how we are going to write it. All right. So we are going to write, if the value combination is 0 0 0 for this row, my product term is going to be x bar, y bar, z bar. For example, 0 1 1, it will be x bar, y z. Why? Because the y has a true value, so we'll take uncomplemented form of it. Similar for the z, this. Okay. Now next we introduce a symbol for them, for each of the product term. Okay. So x bar, y bar, z bar, we call it m0. Just by convention, we call it m0. X bar, y bar, z is m1, then m2, m3, m4. So here is a thing you need to understand, right? If you look at this index, right, this subscript index of each symbol, it basically, what we are writing down is the decimal value represented by the 3-bit, isn't it? 0 0 0 is 0, for example, 1 0 0 is 4, 1 1 0 is 6, 1 1 1 is 7, so 1 1 1 is m7, right? 1 1 1 with a binary represent that decimal 7, so we put that 7 as a subscript of this symbol and make it a m7. Okay, this is how we create or we write the symbol, which means a product term like this. So whenever if I call, okay, min term 3, m3 for a function xyz, we already know that min term means a Boolean term which is x bar yz, or min term 5, which means it's x y bar z. Okay, so that's the notion of it, right? A symbol represents a product term corresponding. All right, now let's see how we are going to write this function in a compact form. So what we do, we basically write the function like this: f x y z equals, now we pick up those product term for which the function value is 1. So we pick up x bar, y bar, z bar. Then we pick up this row, row number 2, like if we index like 0 1 2, like this row number 2 is basically x bar, y, z bar, and then another one is row number 5, which is x, y bar, z, and row number 7, which is like x, y, z. So our expression is your x bar, y bar, z bar or x bar y z bar. So we are picking a product term where the function value is 1 and oring them, okay, or xy bar z and or xyz, right? So this is a 4 term or, like there are 3 OR operation between 4 Boolean terms and so on and so forth. So this is my function. Now we can further make this function compact. So if you recall, by definition, these product terms are the mean terms, isn't it? Like the mean term, by definition, it includes all the variables of the function exactly once, either complemented or in uncomplemented form. So these product terms is really your mean term for us, and this is one way of writing it. And then we replace this mean term or the product term as its symbols. Like this guy become m0, x bar y by yz bar is m2, and so on and so forth. So practically, if you want to write it down, you can straight write it down as that function as m0 or m2 or m5 or m7. We can further compact this expression by using the sigma notation. Sigma is sum for the Boolean algebraic domain. We borrow this in the digital domain. We call it a sum, means really the OR operations. Now m of 0, 1, 0, 2, 5, 7. So whenever you see this form, this compact form, sigma of m0 to 5, 7, you automatically know for this given function, it's basically m0 or m2 or m5 or m7, which we can expand by, we know what is the definition of m0. It is nothing but x bar, y bar, z bar in this context. And then m2 is basically your x bar, y, z bar. M5 is your x, y bar, z, and m7 is x, y, z. So we can start expanding from here to here to here. Okay. So now you see this standard form of sum of product, like that way of expressing a Boolean function would be something like this. You got a truth table, look at where the function value is 1, and do write sigma m of those subscript values, right? So this guy will become my sigma of m0, 2, 5, and 7. Okay, so that is how you write your sum of product expression. Sum of product expression in most compact form using the sigma notation.